In the last section, we analyzed the small signal transfer function of DCM converters. The analysis is based on the approximation that the inductance is small and can be ignored. So you might be curious about how accurate is this approximation. So in this section, we are going to compare the accurate analysis and the previously approximated analysis. So we are going to look at the accurate transfer function for DCM. Accurate here means we no longer approximate L to be 0, right? So with no approximation of L. The small signal DCM transfer function indeed has the same format as the CCM. Has identical format with continuous conduction mode. So remember, when we analyze the CCM operation, right? First, let's have a review of CCM. So the GVD for CCM, it has such a format, right? GD0 times 1 minus S over omega 0 times 1 plus SQ0 omega 0 plus S over omega 0 squared. So this is a single right half plane 0 and a pair of poles, right? A pair of poles. Usually the Q is large. So if Q is larger than 1 over 2, 0.5, then we will have quadratic pole response. Meaning that we have a pair of complex poles, which are conjugate, right? Conjugate. And for the CCM, GVG equals to GG0, 1 over 1 plus So it's like a pair of poles, right? And there is no right half plane 0. So previously, when we analyzed the DCM, both functions are only single pole response, right? But which is based on the assumption that L is ignored. If we consider no longer approximation of L, then the DCM analysis will be pretty similar to the CCM. So I'd like to first give you the results such that you can have a basic idea about how it behaves. Then we can analyze it. So for example, GVD for DCM with accurate analysis will have such a result, GD0 times 1 over S over omega Z. And here is the still the second order equation here, but Q is smaller, right? Much, much smaller than 1 over 2. So we will have two separate poles. So for this case, namely that Q is very small. Two well separated poles. And for DCM, GVG, it has the similar format as the CCM. And also two well-separated poles, meaning one low-frequency pole and one high-frequency pole. And moreover, for GVD transfer function, this right half plane 0 still exists, but with high frequency. Okay. So basically, the difference, where does the difference come from, right? So actually, the difference still origins from that the L is pretty small in DCM, right? L is small in DCM. So this makes that we will have three phenomena. First one is that the right half plane 0. As I mentioned here, right? Our right half plane 0 of DCM is pushed to high frequency. Usually, this frequency is very high, which is even higher than the switching frequency. Fs. And second phenomena is that two separate poles, right? The high frequency pole also appears at a very high frequency. So one pole appears at high frequency. So this is not higher than switching frequency, but usually it's close, right? Close to switching frequency. So which is usually tens kilohertz or even hundreds kilohertz, right? So thirdly, so if we are only considering the low frequency behavior, so the DCM essentially exhibits a single pole response. This means that our previously approximation maintained good accuracy at a low frequency analysis. So to show you how accurate this is, we can give you a specific example of the body plot of a boost converter. So example here, body plot of boost in DCM. So this example comes from the textbook. So in the textbook, they have the specific parameters for the boost example. So we look at the GVD performance body plot of the boost in DCM. So frequency axis and GVD magnitude plot. Suppose here is minus 20 dB, 0 dB, 20, 40. For that numerical example, if we adopt the approximation with ignoring L, we can plot its body plot very conveniently. You will see that its body plot will be like this, single pole response. So here is the pole position, right? Pole position, FP. And after this pole, the magnitude plot will decrease at the slope of minus 20 dB per decade. And for the phase plot, we mark here is 0 degree, minus 90 degree, minus 180 degree. The phase angle, GVD, for the boost in DCM. For the approximated result, you will see that the phase plot will have such a shape, right? So begin to change at 1/10 of FP. And reach minus 90 degree at 10 times FP. That's the phase plot, right? So then here comes the comparison, right? This, you will see that this is only the approximated results. How about the accurate analysis? Right, lucky enough, we have powerful simulation tools to analyze the body plot, right? So we can, I will plot the accurate result on top of this plane to show you the difference. You will see that this is the accurate results, right? Pretty close. Only difference that at high frequency here, it separated a little bit, right? So usually the frequency here is pretty high, like 50 kilohertz, 100 kilohertz. Meaning that below this range, the approximation maintains good accuracy. For the phase plot, it's roughly the same, right? Roughly the same. So like here begins to separate it, right? Separately. So it's like the second pole at close to the switching frequency begins to have its impact, right? And with even higher frequency, the 0 will also have its effect. But overall, for low frequency range, the approximation is pretty accurate. Okay, so in this section, we have compared the pole and 0 distribution of the CCM transfer function and also DCM transfer function. So in comparison with the CCM, we can see that DCM push one pole to and 1, 0 to high frequency, so that the dynamic response of DCM operation is much simpler than CCM.